So now that we learn how to assign oxidation numbers, we want to look at how to balance redox equations. So balancing redox reactions is a little different than the standard balancing of chemical equations. Usually we do a trial and error process, but with redox equations, they're commonly done in terms of the reaction itself in either acidic or basic environment, meaning that you have an excess proton or excess hydroxide solutions. And this is needed because the reaction is always done in the presence of water and ions because those will conduct electricity. So that's a requirement of the reaction. Now, because all of these, sort of reaction components are always there, sometimes they're involved in the reaction, sometimes they're not, but a lot of times these components are not included in the actual equation. So a lot of times what you'll be given is the net ionic form of the equations, which don't have some of these protons or hydroxide or water included in it. And as a result, as part of the balancing process, you have to add these components in. And that's why balancing of redox equations is a little bit more difficult. So there's steps to this balancing. Some of you might have seen it before, some of you might not, but we follow this pretty prescribed step. And as long as you follow them, you always be able to balance your equation. And in the end, you can always double check to make sure that you have a balanced equation. So the first step is always to separate out the equation that you have into oxidation and reduction, what we call half reactions. So we're basically saying that which part of that reaction is just the oxidation part and which part of the reaction is just the reduction part. And the way we do that is by assigning the oxidation number and then determining who gets reduced and who gets oxidized. And then once you have those two half equations, then what you want to do is follow these four steps here, which means you're balancing them using this sequentially. So first you balance everything that is not hydrogen or oxygen, and then you balance the oxygen, then you balance the hydrogen, then you balance the electrons for charges. So I'm going to show you examples of this. This is just a quick overview of it. And then after everything is done, you're going to multiply the two equations in such a way that the number of electrons are equal for both half reactions. The reason is, as I said before in the prior video, it's not possible for a redox reaction to occur if one reactant, gives away, let's say, 10 electrons, the other reactant only accepts 6 electrons, for example. If a reactant gives away 10 electrons, the other reactant has also have to accept 10 electrons. Okay, so this is when that multiplication to equalize the number of electrons become necessary. And then after everything is equalized, you can add the half equations back together to form the overall equations. And then at the end, just check that they're balanced. This is the step you would do if you're dealing with an acidic environment. If you're dealing with a basic environment, you're doing the same exact steps that at the end, you're going to add two more steps where you add hydroxides to knock out all the protons that you have in the equations, because in a basic environment, protons don't really exist. And then afterwards, you just double check again to make sure your equation is balanced. Okay, so I'm going to show you two examples here. They're pretty complex examples of balancing. See, once you are able to do equations like this, you should be able to do other redox equation. So we're going to take a look at the first one here, which is ClO3 minus plus As2S3 goes to chloride H2ASO4 minus SO4 2 minus. The key about redox reaction is always to keep track of all the charges along with just the chemical formula. I've seen it so many times that people write the formula but forget the charges. And if you forget the charges, then it's going to be a big issue, because then you're not going to be able to balance it correctly. So let's take a look at that first one. I wrote it at the top there. So the first thing that I wrote is just the equation itself. So you can forget all the green numbers there for now. Just the equation itself, right? Which is written in black. And then what I do, the second step, is to assign oxidation states, because I need to know who's oxidized and who's reduced, because my first step is to separate these out into oxidation and reduction half reactions. So for me to be able to do that, I need to know who's oxidized and who's reduced. So those green numbers that are circled on the top are the actual oxidation states of each of the elements. So for example, just to take the chloride ion as an example, here I started with my oxygen being -2, right? And I know that oxygen is always -2. And so since there's 3 oxygen, it's going to be -6. The total charge of this ion is -1. So that means that the chlorine has to be +5 for the entire ion to have a charge of -1. And that's how I determined that for the chloride ion. You can similarly do that for the rest of these other species that are shown here. And hopefully that's not too difficult for you to do. Once we do that, then what we want to do is just look at those circled numbers at the top. Remember, the numbers at the bottom are the actual total charge that I calculated based on the number of oxidation state of each element multiplied by how many elements there are. Those numbers are not the oxidation state. It's the top number, those circled numbers that are the oxidation state. So if you look there, you can see that the chlorine has gone from +5 to -1. That tells me that chlorine is reduced. So I'm going to start with my reduction reaction. And when I started, all I wrote down was just ClO3 minus goes to Cl minus. Okay, so forget the H plus, the H2O, and the electrons there. I'm just doing the ClO3 minus going to Cl minus. And then I also noticed that the arsenic, As, goes from +3 to +5, so that's oxidation. The sulfur goes from -2 to +6, so that's also an oxidation. So the first thing I wrote on the oxidation half reaction is As2S3 goes to this and that. Again, no coefficients at that point. It's just that those three species written everything with coefficient of 1 because we haven't balanced yet. Okay, so that would be the half reaction. And then I start balancing each of the half reactions. So I go to the reduction half reaction, and then I say, are the atoms, the elements that are not hydrogen and not oxygen already balanced? So I have chlorine on both sides. Both of them are 1. So that means it's balanced. So again, imagine that I only have ClO3 minus and Cl minus. The chlorine's already balanced. Now the next step is the oxygen. The oxygen, there's 3 on the left side. There's none on the right side. So I have to add water to balance out my oxygen. In this case, I need to add 3 water. And that's why that 3 water is there, because that will give me 3 oxygens, right? And then once I balance that out, then I have 6H on the right side. But I don't have any H yet on the left side, so I have to balance that out by adding proton. So that's why the 6 proton is added to the left side. And then lastly, I look at charges. So I have a +6 on this one. Each proton is +1. There's 6 proton. I have -1 on this one. So +6 and -1 gives me +5. On the right side, I have -1. So therefore, to balance everything out, I need to add 6 electrons to the left side. Now, why 6 electron? Because electrons are -1. So if I add 6 electrons, that means -6. Then that would give me a balanced charge. Both sides have a charge of -1. This is always one of those things that I need to emphasize. When I say I need balanced charges on both sides, I don't mean both sides have to have a total charge of 0. I mean both sides have to have the same total charge. In this case, both sides have a total charge of -1. Now that I've completed my reduction half reaction, I'm going to jump into my oxidation half reaction. In my oxidation half reaction, I'm starting only with the parts that I circle in yellow without any coefficients to begin with. And then what I want to do is, again, balance everything that is not hydrogen or oxygen. So I have 2 arsenic, I have 3 sulfur. I'm going to need to balance those out with the right side. So that's why I put the 2 and the 3 on each of those species. That would balance them out. Now, once I do that, I need to balance my oxygen. So I counted that I have 4 times 2, which is 8 oxygen, and then 4 times 3, which is 12. So in total, 8 plus 12 is 20 oxygens. I need to add 20 water to balance that out. That's why this 20 water appears here, okay? After I do that, now I have H plus to balance. So for the H, to balance that out, I have 40 H on the left side. I only have 4 on the right side, so that means I'm going to need 36 more H plus, right, to balance that out. And that's where that 36 H plus comes about, okay? The last part is to balance charges. For that, I'm going to need to calculate all the charges on the left and the right. On the left, I have 0 and 0 here. These are both neutral molecules. On the right side, currently I have -2. 3 times -2 is -6, and I have plus 36. So if I count that, I have 28 plus charge on the right side. I have 0 on the left. So to balance that out, I'm going to need to add 28 electron, and that's where that number comes from. Okay? And then so once I have all that, then the next step is I need to equalize the number of electrons. So remember that the electrons that are given away has to match the electrons that are being accepted. So currently, if I just look at the number of electrons, I have 6 electrons for the reduction. I have 28 electrons for the oxidation. So those things don't match. So my goal is to find numbers that I can multiply here that would allow the electrons to be equal to each other. And so basically what I find here is lowest common multiple of 28 and 6, and that would be 3 and 14. So once I do that, then I would multiply basically all the top equation with 14 and all the bottom equation with 3, and then I will add them together to get back my overall equation. Okay, so if you do that, I'll do it really quickly here in an overall view here at the top. So 14 times 6 electron is going to give me 84 electron. 14 times 6 proton is going to give me 84 protons. 14 times 1 chlorate is going to give me 14 chlorate. 60 water here because it's 3 times 20. And then 3 times As2S3 is going to give me 3 As2S3. And then hopefully you can work out the product side as well with those multiplication. If you do this correctly, one of the things that should always cancel out is the electron, because we made it that way. We made it so the electrons are equal to each other and they're on opposite sides, right? Because one is oxidation, the other one is reduction. So the electrons, as you can see, both are 84 electrons, so we cancel that away. And then usually there are some species that are identical on both sides, so you can cancel those out. So if I look here, the H+, there's H pluses on both sides. There's 84 on this side, there's 108 on this side, so 108 minus 84 should give you 24 H plus that's left on the right side. All the ones on the left is gone. And then the water, 60 on the left, 42 on the right, so all the 42 disappears. We are left with 18 on the left. So at the end, this is your balance equation. What you should do at that point is double check to make sure that everything looks correct. So 14 chlorine here, and then we got oxygen. We got 14 times 3, that's 42. And then we got 18 here of oxygen. So 42 plus 18 is 60. On the right side, we do 6 times 4 here, that's 24. And then 9 times 4 is 36. So 24 plus 36 is also 60, so the oxygen is also balanced. The hydrogen, we have 18 times 2, so that's 36. On the right side, we have 6 times 2 here, that's 12. And then we have 24. 24 plus 12 is 36, so that matches. And then the As and the sulfur both also match. Okay, so everything looks great in terms of the elements. Now we have to check charges. So that's almost always the step that people tend to forget. So if you look at charges, I'm going to use a green color here just to help distinguish. So the charges on the left is negative 14 because I have 14 chloride. Each chloride is negative 1, so that's why it's negative 14. This guy is 0 because water is 0. This guy is also 0. So on the left, I have a total charge of negative 14. So if the equation is balanced on the right side, I should also have a total charge of negative 14. Chloride ion, 14 of them, so that's negative 14. We have this H2ASO4 minus, okay, so there is a minus there, so 6 of them, so that's negative 6. I have negative 2, there's 9 of that, so that's negative 18. And then I have positive 1, I have 24 of this, so that's positive 24. So 24, 18, 6 cancel away, so I'm left with negative 14 on the right as well. So negative 14, so that match, okay? And that's the end of my balancing. Now, how do I know to stop there? Because I could have acidic or basic. Well, I know this is acidic because I have an acid that's present there, H2ASO4. That might not be an acid that you immediately recognize, but notice that how AS is a group 5 element, and it's basically the same as this acid right here, which is hopefully something you recognize as an acid from our discussion of acid-base chemistry, okay? That's number one. You can see that it's quite a bit more steps to balance compared to your standard balancing using trial and error, okay? So the second question is the one shown here. S2 plus MnO4 minus goes to S8, MnO2, and OH minus. So This one, you immediately see that there's OH minus there, so that tells you that that's base condition, so I have to balance it using the basic steps, which just is the same as the acidic steps, except you add a couple more steps at the end. Okay, so a lot of times you would have to look through the reaction to help you figure out whether it's acidic or basic condition. Sometimes you'll be given that. You'll just be told that balanced is in acidic condition or balanced is in basic condition. Okay, I'm going to start here with the balancing of the second one. I'm going to go through it a little faster. So same way, I started with the reaction itself, nothing written on it. And then afterwards, I started assigning oxidation numbers. So those are all the green numbers there at the top. They're circled. Once I assign the oxidation number, I find that the sulfide, which is S2 minus, is oxidized to sulfur. And so that's my oxidation reaction. And then my reduction reaction is MnO4 minus going to MnO2. Notice that I didn't include the OH minus anywhere. And that's because it's not part of the actual thing that is being oxidized or reduced. So in the half reaction, really all you're focusing on is the thing that undergoes the oxidation or the thing that undergoes the reduction. Now you want to include everything that's part of that species. So for example, like MnO2, the oxygen is included in writing the formula, but I don't need to include the OH here because the OH is not, oxidized or reduced. It's just telling me that that's the condition. As you'll see, eventually the OH will be included at the final equation when it's all balanced, because as part of the balancing, we do add hydroxide to the last step in a basic condition. So you never have to worry about not including something like an OH or an H plus or water, because those are part of your balancing steps. Okay, so keep that in mind when you are balancing redox reaction. So again, I started initially with just this and that, and then I noticed that I need to have 8 of this, so I put the 8 in front of it. Once I have 8 there, I don't need to balance oxygen or hydrogen here because they're not present in this equation, but I do need to balance the charges, so I add 16 electrons on the right side, and that balances that top equation. At the bottom, initially all I have is this and that, and I can see the manganese is already balanced. To balance the oxygen, I'm going to add 2 water, which is why that's there. And then to balance out the proton to hydrogens, I need to add 4 protons. That's why that's there. And then to balance out the charges, I need to add 3 more electrons, okay? Because on the right side, I have a charge of 0. On the left side, before I added this, I have plus 3. That's why it's 3 electrons that's added, okay? And then again, finding the lowest common multiple so that the electrons are equal to each other, and that is 3 and 16, okay? I multiplied all the equations on the top with 3, multiply all the equations at the bottom with 16, and then I wrote the overall equation right here, okay? So just pay attention to this one first right now, okay? Just pay attention to that one first, that whole equation that I just circled. That's just from adding and multiplying each equation with the 3 and the 16, and then adding them. And you notice that the electrons are already canceled, right? Because again, if you do this correctly, the electrons always have to cancel. Now, once we're there, the equation is already balanced, actually, this thing that I circled in yellow. But remember that what we're being asked is to balance this in base, not in acid. Right now, we're balancing in an acid. How do I know? Because there's H plus there, okay? That's the sign that this is an acidic environment. So how do I get rid of the H plus? I'm going to have to do the next 2 steps. That is base balancing, okay? And that is to add hydroxide. How much hydroxide do I add? I add exactly the same number of hydroxide as I have for my H plus. So since I have 64 H plus, I'm going to add 64 hydroxide to the left side. Now, because of conservation of mass and conservation of charge, I can't add just 64 hydroxide to one side without adding the same number to the other side. That's why I'm adding the 64 hydroxide to the right side also. Once I do that, this is what happens. Everything remains the same with the exception of this. The 64 H plus and 64 OH minus, H plus OH minus becomes water. So since there's 64 of these guys, then it becomes 64 water, okay? The 64 hydroxide on the other side is just part of that new equation, so it's just 64 hydroxide. But once you see these equations are added, you see that there's water on both sides, there's more water on the left side, So therefore, all of these disappear, and there's 32 that's left on the left side. So this here would be your final balance equation in a base condition. So you see that there's no more H plus there. We have OH minus though. And so that's why I told you at the beginning, don't worry about that hydroxide that you didn't include in the half reaction, because it does reappear at the end, just because the hydroxide is part of the balancing step. Okay?